In this lecture, we're going to talk about individual cases, thinking about outliers and influence, because we want to make sure that if individual cases are really disturbing our conclusions, we want to be aware of it. We're going to begin by talking about what is an outlier. The basic idea and intuition of an outlier is probably something you're comfortable with, but we need to be a little bit clearer on exactly what we mean in a regression model context. And what we mean by outlier is a particular observation or case that does not follow the same model mean function as the other cases. And so I've tried to represent that here mathematically, that all of the other cases denoted by subject J or index J for just generality has the usual linear mean function. The average value of the response as a function of the predictor variables is simply a linear combination of the predictor information and the beta parameters. That's what this xj transpose beta means. It just means there's a nice linear function connecting the predictor information to the mean function. Except for a particular case I, and in this case we have that same mean function for subject I, except it's off by a shift, an amount delta. So the mean function for case I is not a simple linear combination like it is for everyone else. It is that linear combination, but shifted by a fixed amount, so that the mean function is not the same for case I as it is for all of the other cases indicated by subscript J. One of the ways that we measure outliers is through the residual. A lot of times if a response observation is very atypical and is offed by a shift delta, we'll be able to see it manifest itself through the residuals. And so there's a couple of different kinds of residuals. The first one we're going to talk about is a standardized residual. That's R subscript I for the ith case. And standardized residual is simply the observed residual for that case divided by the standard error of that residual. So this is just a standardized variable. We take the variable amount, EI hat, and we divide by a measure of variation of EI hat, and we get something that is on a average of 0, standard deviation or variance of 1, and we have standardized variable. Notice that this formula involves a measure of variation from all of the residuals. Sigma hat, remember, is based on the residual sums of squares, which uses all of the data residuals. And it's also specific to the leverage value for a particular case, the HII. And remember, leverage is measured from the predictor information for case I. So what makes the standardized residual for a case is not only the observed residual for that case, the residuals for all the other cases, to build in the standardization, but also the predicting information. A very similar kind of residual with a very similar kind of name is called the studentized residual. And if you look at the formula for it, it's denoted TI, and the formula for it is almost the same as for a standardized residual. The only difference is that you will notice that the sigma hat has a subscript with parentheses I, and that refers to the fact that the measure of residual variation, the residual sums of squares in this case, does not include case I in the computation. So this refers to a sigma hat estimate without case I being used. And you can imagine these are very similar kinds of statistics. They're very similar in value. They'll just differ by whether or not that case was used to make the variation. we can form a test for a particular case being an outlier or not. Null hypothesis is that case I is not an outlier, and the alternative is that it is an outlier, and we can specify that through this shift parameter, delta being equal to 0 in the null hypothesis, and in the alternative that the delta is not 0, meaning it's an outlier. The test statistic is just the studentized residual, and because it's a two-sided test, we will calculate the p-value by calculating the probability and so the test is based on this studentized residual, and the appropriate degrees of freedom for this is going to be n observations total minus the number of beta parameters that are in the model, including the intercept, that's p prime. And then we subtract off one more because we don't use observation I in the computation. And this would be how we'd get an appropriate p-value. So again, to summarize, if you have case I suspected to be an outlier in advance, you use the externally studentized residual and you compare it to the degrees of freedom that I've mentioned. The thing that's important to know is in the second bullet that this is very uncommon, and we usually don't do things this way. We usually don't know in advance before the data is examined that case I is going to be an outlier. Usually the problem is we look at plots and we see something weird for case I. And if that is the case, after looking at data, then you need to follow this kind of procedure. Really what you've done then is gone through and found the value of the outlier test statistic and absolute value, and you've looked for the biggest one. And so you're interested. So the thing we need to realize is what we've done is look through the data and found the biggest value of the statistic. And when we have done that, that means that the usual t probability distribution is not the correct one. We need to do something else. And to see it, just think about the things I'm talking about here in bullets 2 and in 3. Remember that when you do a test and the null hypothesis is actually true, you have and you decide that a 0.05 significance level is what you're going to do to have doubts about the null hypothesis. You need to realize that if you do 100 such tests when the null hypothesis is true, you will incorrectly judge about 5 of them, 5 out of 100, to be troublesome false null hypotheses, and you'll incorrectly say that there's a problem with them, just because occasionally data by probability will turn out to be unusual. When that is the case, if you look at bullet 3, if you've got 65 observations, you got 4 beta parameters in your model, the probability that you'll get a t-statistic with 60 degrees of freedom exceeding 2 in absolute value is 0.05 in probability. But if you look through the biggest out of the 65 statistical tests, the probability you'll get one above, you'll get a test that will have a test statistic above 2 in absolute value is almost certain. So what this tells us is that even when data are behaving normally, like they should according to the probability rules, it is almost certain that you will get a residual that will look unusual according to a t-distribution. Even when there's nothing really wrong with it at all, just from normal probability sampling, you will occasionally see an unusual residual and outlier t-statistic. It's almost certain to happen if you have any kind of a big data set. And that means what we need to do is we need to adjust this testing procedure to account for the fact that we're going to have things happen like this. We need to change the procedure so that the type 1 error rate is closer to 0.05. And that means we basically need to have a smaller p-value occur in order to make a judgment that we would have doubts about the null hypothesis of a case not being an outlier. Remember that a type 1 error is rejecting the null hypothesis when the null hypothesis is true. And the way we typically do this adjustment is to use the Bonferroni inequality. What we know is that the chance of falsely labeling at least one case an outlier is less than or equal to n times alpha, where alpha is the usual 0.05 probability cutoff for doubting the null hypothesis. And that means that if this probability is less than or equal to n alpha, if we want the entire probability to be something like alpha, we need to divide this chance by n, and that means we would need to have a much more stringent p-value cutoff for judging something to be an outlier. For 65 observations here in the second bullet, I point out that it would be something like about a 0.001 p-value would be needed in order to have about the right error rate. And so this Bonferroni correction is done automatically in R using one of our outlier test functions. And that's how we'll do outlier tests. This particular overhead 9 shows how to use some of the R output in order to calculate the standard and studentized residuals. And this really is just using the definitions of keeping a residual, dividing by sigma hat, and the leverage. And this is really only of interest for people that want to try to look at the programming. I'm going to move on to overhead 10 that shows you the outlier test command that imposes the Bonferroni p-value. In this particular case, I've estimated a regression model called M1, and when we look through the residuals and do an outlier test on our biggest residual and absolute value, the studentized residual is about 12.4. That is a very unusual studentized residual, and the Bonferroni p-value is amazingly small. So very clear evidence that case 12 is in fact an outlier in this model, and that the mean function is just been shifted. It's not the same as the other cases. Remember, it's the outlier test function based on a model that you will use to examine after the fact whether a particular case is an outlier. And then once you've located outliers and done an outlier examination, if you find something, what should we do about it? Clearly, you'd want to look back through your data, like here in bullet 3, and make sure there's no data entry errors or some sort of definitional errors that have occurred. It is also frequently done that you would maybe analyze the data set with and without a particular outlier and report the results and changes in conclusions depending on whether that particular outlier is included or not. That would be a very responsible thing to do in a statistical report. No matter what, you're going to try to find out why a particular outlier occurred. Was it a particular data collection operator or computer system? Why did the outlier happen? Some of the great advancements in human history have been outliers, and observing and studying why they happened have led to a lot of the great advances in human history. On the last bullet, I point out that for some reason, students and scientists and researchers like to get rid of outliers. And that's really not the right way to go about things. You want to keep your outliers and just document their impact. They're data that you thought were worthy of being in your study beforehand. You had no reason to remove them. And I think without amazingly good justification from an unbiased point of view, you want to keep all data. It's important. Another issue besides outliers is to measure the impact that potential individual cases might have on estimates. Just because an observation is weird, like an outlier, is one issue, but really the more important issue is what does a particular case do to our estimates and our conclusions? And one main method for doing that is a particular measure called Cook's distance. D with a subscript I is Cook's distance. And really what it is the distance between the estimated beta vector that uses all of the data and the estimated beta vector that removes case I from the computation. How different is the reduced set data beta hat from the full data beta hat? And so we have a kind of quadratic squared distance between those two beta vectors here, scaled by the predicting information distance matrix. And so we come up with a kind of distance. How far is one of these vectors from the other? If they are far apart, and Cook's distance is big, it means that the particular case has an important impact and changes the parameter estimate vector a lot. Small values of Cook's distance imply that there really is not much of a change in the betas, and therefore probably not much impact on conclusions. Another way to write Cook's distance is not so intuitively apparent. This is clear what we are doing. We're measuring the distance from one beta vector to another. On overhead 13, you can see that we've re-expressed Cook's distance in terms of its components. And you can see that the main components are the standardized residual, the R sub I squared, and also the leverage, the HII. And so what goes into making an important influential case? Well, influence comes from the residual. What is the response value for this case? And it also has a lot to do with what the predictor values are for this case. And you can see that if you have a very large leverage, a very weird case with respect to the predictors, you're going to tend to have a very big Cook's distance. So in the first bullet, we notice that Cook's distance is a mix of standardized, residual, and leverage. Remember, leverage ranges from 0 to 1, 1 being more unusual. The problem with Cook's distance is that there really isn't a standard scale for what makes a big or a small Cook's distance. Bigger, of course, is more influential, but there really isn't an absolute number that says, oh, that's a big Cook's distance. A big Cook's distance changes for every problem. It depends on the sample size. It depends on other data set characteristics. What we usually do is we look at our Cook's distance and we try to observe cases that have abnormally big Cook's distances. They will be ones that might have important impacts on our conclusions. Even if we can't really say what is a value that's big, we look at them relative to the rest of the Cook's distances in the data set. Every observation has a Cook's distance, so there are n of them, and we would look at the most unusually large ones. Certainly, Cook's distances that are above a half are typically going to be obviously as large and worthy of our special consideration about what they do to our conclusions. Here's a little example of a animal study studying the amount of drug that is present in livers of rats. We have the liver weight, we have the body weight of the rat, we have the dosage of the drug that was given to the rat, and so that's the multiple regression set of predictors. And then the amount of drug in the liver is the response Y, and we relate Y to the predictors through a multiple regression model here. And then on the next page we show a panel of residual characteristics called the influence index plot for the model that we just made. And you will notice that we see a panel of Cook's distances at the top. The second row in this grid is the studentized residuals. The next one down, the third one down, are the Bonferroni outlier test p-values. And finally, in the last row, the hat matrix values, the leverages. And so what you would observe from the Cook's distance display is an unusually large Cook's distance for case 3. None of the others are noteworthy. For the studentized residuals, you will notice that really there aren't any residuals that are particularly strange here. They're all between about plus and minus 2, like we'd expect. And that's carried out here by looking at the Bonferroni p-values, and none of them are small at all. Case 19 is the smallest, but that p-value is like 0.96, and so no evidence at all that case 19 would be anything like an outlier. For the leverages, which again measure predictor characteristics, you can see that case 3 is quite abnormally large leverage, and so it's not too surprising that case 3 has an unusually large Cook's distance, because after all, the leverage HII is a component of the Cook's distance. Remember that ID.N equals 3 means show us case labels for about 3 of the most unusual points in the display.